Gordon. So Gordon McCord will be chairing this panel. He's an associate teaching professor at the School of Global Policy and Strategy at UC San Diego. His work is at the intersection of development, health, and environment, often using spatial data and analysis. He's also a SIGA affiliate. So welcome, Gordon. And I'll hand it off to you to introduce our two discussants. And also note that we have a video presentation coming after this panel that will tail end the session that's coming from Hai An Deng at the World Bank. Take it away, Gordon.
Excellent. Thank you, Sam, and thank you, SIGA, for organizing a great conference. So welcome to the panel on health data and the environment. We're showcasing a few papers that use large survey or administrative data sets to look at the health-environment interface, and we're excited to share these with you. Really because it's only been in the last few years, decade or so, that we've got compiled internationally comparable survey data or administrative data that are allowing for a battery of papers that have come out that are exploring and detecting generalizable global relationships and how health and the environment are related. And so we've got three great examples of papers like that today. I'll present in first, just going by the agenda. After that, Jesse Antilla Hughes from the University of San Francisco will give a talk, and then Tama Carlton from the University of California in Santa Barbara. And thanks to the two of you for joining us today. And then, as Sam said, we'll have a presentation, an asynchronous presentation by video. So I will go first. Let me share my screen here. All right, and this is joint work with Jesse, in fact, as well as Amir Jina at the University of Chicago. And I'll be talking about how the El Nino Southern Oscillation phenomenon helps drive child undernutrition in the global tropics. So ENSO, most of you, I'm guessing, have heard of it. It's one of the major drivers of interannual weather variation. The planet oscillates between being in a neutral state to the El Nino state to the La Nina state. And it's really one of the principal modes of climate after intra-annual seasonality. You get changes in temperature in the tropical Pacific, and that changes weather patterns across the world with the El Nino state, which is when the tropical Pacific is warmer, leading to drying in most places, particularly in the tropics. And then the La Nina state, which is when the tropical Pacific is cooler than the neutral state, bringing cooler and wetter conditions in much of the tropics. And importantly, for at least thinking about the econometric specifications and the plausible conditional exogeneity of the timing of El Nino, that even though this is a quasi-periodic phenomenon, there's a lot of randomness and there's a stochastic element in the timing of this, which is quite important. These come roughly every 3 to 7 years, but there's a lot of randomness in that timing. There's been a lot of work relating ENSO to child nutrition. So first, work on ENSO itself and its direct effects. Lots of papers on how it affects agriculture in the tropics, economic production in the tropics, social stability and conflict. But then directly health effects, lots of reasons to think that it affects vector and waterborne diseases, and measuring that very, very carefully with these changing weather patterns, affecting health indirectly through changes in agricultural output, as well as affecting health indirectly through conflict and other social instability. So lots of reasons to expect that this relationship between ENSO and child health. The empirical approach will use the demographic and health surveys, which have been alluded to earlier in a few talks. And this is really, I think, the first at the kind of large scale internationally comparable set of health data that have been exploited by social scientists and health economists to understand a lot of these relationships. So we've got 186 DHS surveys that we're going to be using across 51 countries. So this map, which shows you where the DHS has coverage of these surveys. We're not using all of these countries. We're going to focus on the 51 of them that are actually teleconnected to the ENSO phenomenon, which means that when there's a change in the temperature of the tropical Pacific, there's a statistically significant relationship to the weather in this particular country. And so for those 51 ENSO teleconnected countries, we're working with about 1.3 million children in that sample. And the countries contain about 48% of the world's under 5 population. So we're really excited to be able to bring all of these data together and make statements about the relationship between this planetary phenomenon, which I haven't said so far is predictable up to about 6 months or so, and the variation in child health for a good part of the human family. The measurement of the ENSO state of the planet is done by looking at the sea surface temperature of the tropical Pacific, and there's several ways to do that. So looking at the different parts of the Pacific here, what you see are how different scholars have measured different temperatures. We're using the most commonly used one, and particularly for the paper by Saosheng, Kaiyomeng, and Mark Kane to studying El Nino and conflict. It's this Nino 3.4 estimate, which is this part of the tropical Pacific, and correlating that to what's going on with weather and then health in other parts of the planet. And so here you see what the raw data look like. So this is the state of the sea surface temperature of the tropical Pacific, with blue being the El Nino state and pink being the, blue being the La Nina state and pink being the El Nino state. And so you see this quasi-periodicity, but a lot of stochasticity also in the behavior of this phenomenon. And then this is how the weight for age z-scores of the children in our sample are evolving over time. And we here see the pixel level correlation between that El Nino measurement and temperature and precipitation at the pixel level around the world. And so you see that for this middle map in panel C, red means that it's positively correlated to temperature, and most of the planet warms during El Nino, whereas there's a lot of heterogeneity in terms of precip, that some places dry out and some places become significantly wetter. And we'll learn a lot about what's likely going on here by exploiting this heterogeneity. So the empirical approach is pretty simple. It's you can throw a battery of fixed effects, but basically the key things here are that we're using country fixed effects. We could also use admin1 fixed effects. So nationally, the results are the same. And then dividing the effect of the El Nino between places that have a negative correlation with temperature and those that have a positive correlation with temperature, and looking at those differently. And what you see in the raw data is shown here on the left, which I think is quite powerful and impressive. This is the simple raw data relationship between the distribution of weight for age z-scores in these 1.3 million children in the El Nino state versus the La Nina state. No controls, nothing else here. And so it's amazing just to watch the change in the distribution of weight for age z-scores globally with the temperature of the tropical Pacific. That even in today's day and age, a large part of the human family is just oscillating in its health together with the oscillation of the ENSO state of the planet. And then on the right, you see now the results from these regressions after residualizing all of the fixed effects and the controls that we use, and dividing the sample into the places that have a positive correlation with temperature and a positive correlation with precipitation and a negative correlation with precipitation. So when you're in the El Nino state, do you get more rain or do you get less rain? Most places, so about 90% of the sample, have a negative correlation with temperature. And so that's this green line here. And in those places, when you're in the El Nino state, so you get a warming of the tropical Pacific, the weight for age of children drops. So children are negatively affected in terms of their nutrition status. But in the subset of places where you have the opposite climatological effect going on locally, you get the opposite effect. It's raining more, and here we see that children's health actually improves in these places. And it's quite amazing to watch these things break out so neatly in terms of the local correlation between precipitation and the El Nino state of the planet. And I should preview here that these leads us to believe that the agricultural production channel is probably the dominant first order channel that's driving these effects. Because if you think about the other ones, whether it's the temperature effect on, direct temperature effect on health, or the infectious disease effect, that those would not follow these patterns in terms of how temperature, in terms of how precipitation affects health. We see this not only in weight for age, but we see these patterns between the ENSO state and several other measures of anthropometrics, weight for height, the body mass index, and then the binary variables of WHO classification for whether a child is underweight or wasted. And again, the opposite signs in all the places that have positive precipitation correlation instead of negative precipitation correlation. And then importantly, we see that these have persistent effects on the one anthropometric that you'd expect has slower moving relationships, which is height. And so you see that there's a relationship between a 4- and 5-year-old's height for age with the exposure to the ENSO state of that child back when the child was born, 1-year-old or 2 years old. So short moving relationships in the anthropometrics on weight where the child can recover quickly, but slower moving persistent effects on height, which is exactly what you'd expect from a biological point of view. We note that these effects of ENSO are consistent over time across the 4 decades that we look at, and broadly consistent over region of the world. And so it's important for us to say, look, that even over the last 40, 50 years, there's not a great leap forward in terms of adaptation to this predictable climate phenomenon, which is important to document. How important is all this in terms of magnitude? We go through this thought experiment to illustrate that. First, we look at the last really a bad El Nino phenomenon, which was in 2015. We calculate that in that year, by our estimates, around 6 million children were pushed into underweight status by El Nino. And then we document, taking the estimates from public health nutrition interventions, how many children would have to receive these different nutrition interventions to offset that 2015 El Nino. And you're seeing on the order of 50 to 100 million children would have to receive either complementary food interventions, nutrition education interventions, or multiple micronutrient supplementation in order to offset. So you're talking about really large numbers of children would have to receive some sort of intervention to offset it. And importantly, it roughly sets us back 1 year of the necessary progress we would have to make globally between now and 2030 if we're going to meet the Hunger Sustainable Development Goals. So these are really quantitatively important effects at global scale. And I'll conclude after this slide to say that the paper offers a few contributions. First, that ENSO matters at planetary scale. This is a generalizable relationship over 50 or so countries. That in these countries, temperature and precipitation constraints do bind. So something's going on, that adaptation costs are high. And people, even though you can get a 6-month warning that this is coming, and you know that it comes every 3 to 7 years, nevertheless, it still affects people every year. We think agriculture seems to be the first order channel through which this operates, and that comes from that precipitation relationship that we see. And then we end with just a policy thought that really you could use these kinds of tools and these large data sets to help institutions like the World Food Program and UNICEF and others with a predictable climate phenomenon to have preemptive global policy responses 6 months ahead of time. You know that certain countries are going to get hit, and we could do better in terms of helping adapt those populations to this ENSO phenomenon. So let me stop there, just because I'm out of time, and I'd welcome questions. Let me stop. There are questions in the chat. I don't see any yet, so I will, just to keep us on time, I will hand the microphone over to Jesse, and I'll keep an eye on Q&A in case there are any questions for me. I'm happy to answer them. Jesse, take it away.
Thank you, Gordon. And thank you, everyone at SIGA for organizing. Thank you for attending, everyone. It's good to virtually see you, and I hope you're all doing well as can be. So this paper is related to the one that you just saw on the El Nino effects on child nutrition. It is part of a larger set of papers that I've been working on the climate variability effects on child nutrition in the global tropics. This one is focusing a bit more on mechanisms. And so, the El Nino paper is kind of looking at these large-scale spatiotemporal correlations that are seemingly driven by the ENSO phenomenon, pointing towards agriculture. In this paper, I'm going to offer some evidence that basically this agricultural channel is a big deal, but there's also some short-term sanitation type effects, or seemingly sanitation type effects that are quite interesting that we kind of want to bring to everyone's attention. This paper is with Rachel Baker, who is currently a postdoc at Princeton and is absolutely fantastic, and I believe will be on the market soon. So if you're looking to hire someone who does extremely, extremely good work, just FYI. So along these lines, oh, this is actually one last thing. This has already just been published. So yeah, here we go. So as you know, more or less everyone here doesn't need to be convinced of, especially on this panel, high ambient temperatures are a major threat to global public health. And this comes in a variety of different flavors. There's the acute health effects with which we are all familiar from growing up and being told to be careful of heat stroke and heat exhaustion. This can also then, in certain contexts, increase risk of things like malarial transmission or other types of disease environment problems. Right? There are the mortality effects that we increasingly know are a pretty serious deal, including a bunch of work by Carlton et al. Decomposing this that you'll see after this talk. And so we're aware of both these, these short run effects that are obvious medical type concerns, these mortality effects that we've been able to suss out with bigger and better data sets. And along these lines, we've got multiple literatures now pointing out that the in utero and fertility effects of things like high ambient temperatures are also not to be trifled with. Like really, this is one of these areas. There's been an explosion of work, a variety of people, both on the panel and in the audience today, who've been contributing to it. And this is a major, sort of welfare problem related to with climate change itself, and just the general problem of, poverty in the tropics, et cetera. A critical thing, though, and sort of the part of why a bunch of these papers are all focusing on anthropometrics, is that we actually don't know that much about the chronic exposure effects of high temperatures on health. Right. And this is despite the fact that we've got this wealth of evidence, right, that there's all these indirect effects on socioeconomic factors driven by temperature that we know have to be bad for child health. Right. We know that crops are failing at high temperatures. Right. We know that the disease ecology moves around in really pernicious ways. We know that economic production, including not just ag economic production, can be very heavily impacted. We know that conflict can break out. All these things all point arrows in the direction of bad effects on child health. Right. But to date, we have relatively little systematic sort of work done on this. And one of the things that I'll say to that point is that part of this is that, this is very down in the weeds, but the demographic and health surveys make mortality comparisons fairly easy in the sense that they're very standardizedly coded. But in the actual anthropometrics, it's not as straightforward. And I think, honestly, a very trivial friction here has caused a bunch of this work to kind of get backed up. And so that's all to say, we know that children are particularly vulnerable to high temperatures. Like we know that there's going to be these chronic effects, and children in particular are going to be the ones that are less able to cope because of biological coping mechanisms, like just surface area to volume ratio being different. There's a much higher cost of calorie restriction in children due to like potential stunting and similar, and just differential exposure. A lot of kids are out during the day when it's hot. When we add in the fact that we have generally lower adaptive capacity in a lot of poorer contexts, and these potentially major long-term human capital costs that can result, there's a sort of an obvious reason for us to be focusing on these outcomes. And if we want an official institutionalized region, there's also the SDGs, right? A major SDG is reducing undernutrition, right? And so what do we do in this paper? We're using these same demographic and health surveys data that have popped up multiple times today, including in the last paper. In this case, we're going to be limiting ourselves to sub-Saharan Africa, partly because of high incidence of undernutrition, partly because the DHS data there are particularly rich, and partly just to limit scope so that we have to worry too much about too many different types of other things shifting when we look at, say, urban versus rural. Right. A thing to highlight in this population is that it is chronically underweight, undernourished, and stunted. Right. If this were a world representative average set of WHO Z-scores, we'd be centered at 0. Right. But instead, we're shifted to the left, in particular for the weight for age and height for age Z-scores. This is one of the things that's popped out of doing a bunch of work in this literature, is that really thinking carefully about each one of these different types of parameters and what's going on in the background is important, in the sense that weight for height is a ratio of weight and height. And if children are both low weight and low height, the weight for height scores, check them out, are shifted to the right. Right. So we do see some evidence of this in various places. That's particularly interesting. Also in that El Nino paper. But a sizable portion of the kids, upwards of more than a third, not quite a half, count as stunted in these data. Right. And so, we've got 30 countries in this sample all in. This is 17% of the world's children under 5, as opposed to half of them in the previous paper. But it is 70% of all children in sub-Saharan Africa, or at least representative of them. right? In this paper, we actually limit ourselves to children that's older than 1 year, partly because these mortality effects and fertility effects are A, well documented, and B, honestly pretty extreme. And so I'll show you a little bit of evidence in a couple of slides about how harsh the temperature selection effects are. And because we're specifically trying to really focus on the medium-term nutritional effects, we actually limit the sample to everyone who's over 1 year old. Doing the further limit of above 1 year old, only the geospatial data and anthropometrics required gives us a sample of 192,000 children observed over several decades across these 30 countries. We then just do a straightforward merge with the University of Delaware temperature and precipitation data. Right. And so to kind of speak to the fact that this is, I think, partly a data constraint that has been lowered, partly just because we can now easily and trivially take the direct weight and height data reads from DHS and recalculate our own anthropometrics. We just have some very, very interesting action going on in the cross section here that I want to highlight. Right. So there's a long literature, some of it going back to physical anthropology and the really bad old days of weird eugenicist colonial type anthropology that made a lot of a big deal about like geography and temperature effects on various things, typically focusing on stunting, very much of that eugenicist type thing. And so looking through a bunch of this literature, including a bunch of the old bad stuff, there's basically nothing that quite talks about this strong of a gradient in human weight for temperature. It turns out, maybe you can think about this as one of those like obvious colonial mess ups. The colonial theorists were so obsessed with height and stature, perhaps partly because of the European experience of being undernourished and then growing during the 1800s, that they basically never got weight measurements. It's more difficult to measure the weight of an adult. Regardless, we see a very, very strong gradient here. This is just visible in the raw data. If you go from 20 degrees C to 30 degrees C, you lose a whole standard deviation in weight for height. Right. And so this effect is a pretty serious one, right? We're kind of looking at this thing and we're saying, hey, so you don't have heavyweight kids over in the hotter areas basically at all. And so there's a variety of things in ecology, hominid evolution, and similar. They go back to things like Bergman's rule and Allen's rule. There's sort of like metabolic rules of thumb related to the fact that higher temperatures require more energy shunting. So there might be a prior set of stuff like this that's in that literature, but to our knowledge, this is the first time this has been documented in a cross section with a normal sample of other people on the planet. And so that's the cross-sectional. We then do a standard two-way fixed effects panel decomposition a la climate impacts literature to get the actual effect at different timescales, right? So we aggregate up the University of Delaware temperature data is monthly, so we do basically a crude degree month type approximation, which works out quite well. And in this case, what we're looking at is the marginal effect of an additional month with an average temperature in the bucket that we see here. Right, on the three core, weight for height, weight for age, and height for age z-score measures that we have. Right, and so what do we see going on here? This is basically showing us that the high temperatures, right, are fine up until a certain point and then cause a catastrophic loss in child weight for height, decrease in weight for age, right, and height for age, which in 1-year-olds should be a pretty slow moving measure. We basically see nothing. Right. So note, this is just limiting to the rural areas. If I showed you this graph for the urban areas, it would all be pretty flat lines. So that's a piece of evidence that this might be an agricultural channel thing. B, I think everyone in this audience is familiar with Schlinker and Roberts and subsequent work with Lobel and similar, right? And we're all quite attuned to the fact that this agricultural channel is not a joke, right? And so the fact that this basically seems to be something like a direct calorie pass-through problem where children in rural areas see the crops fail and then they see their weights decline within that year. We're not able to perfectly detangle mechanisms here, but this seems to be suggested. One thing that we can do is we can just look at rural versus urban and then also get timing of heat shocks during different areas, right? And we see that aside from rice, which is very, very infrequently grown in this sample, right, the wheat and maize season growing season effects are much, much more pronounced, right, than the overall average year effect. So at annual level, we're seeing a lot of action in the rural areas that seems to be driving this cross-sectional gradient. It's sort of an interesting part of this is we decided when we were running the paper that we should look at multiple different timescales and control for them at the same time because of the obvious potential for different mechanismic pathways, right? And so we kept getting these very negative effects on the month of survey response in the urban areas. And so with a bunch of work on this, we tied it up, and it's a pretty strong result, and it pushed us into this literature that's been blossoming in the past, maybe 10 years tops, tying high temperature in tropical megacities to outbreaks of diarrhea and similar sanitation issues. Long story short, like microbes are in essence, time is equal to free energy. So if the temperature goes up for a bunch of microbes, just push them into more optimal, faster reproducing areas. So we're getting this as a monthly effect in the urban areas. This seems to comport with diarrhea results that we have, even though the DHS measures are famously noisy for things like diarrhea. And so we have evidence of basically, two distinct channels in this population of children: a short-run urban sanitation adjacent effect, right? If this were a malaria type effect, we would expect to be seeing the monthly effect much more strongly in the rural areas where we're not, right? But then that annual fall off in the rural areas basically doesn't seem to be showing up in the urban kids at all. Regardless of these two possible pathways, we take these things together and do the last step of using random variation and total lifetime average exposure to different temperatures for different children of different ages, taking advantage of the stochasticity of both the child age and the weather itself across multiple different surveys with all these different countries with the fixed effects. Right. And so we see that as we go from the very, very small children to the larger and larger kids at age 3+, right, we're now using that, conditionally random variation lifetime average temperature amongst all 3+-year-olds. And we're recovering a graph that looks very similar, both in terms of magnitude and shape, right, to what we get in that raw cross section. All right, so we do a couple of exercises in this and estimate that something between 60% to 100% of this gradient may be specifically attributable to temperature. So what does it tell us? The major one from our point of view is that these temperature constraints are clearly binding tightly. Maybe this is something a la Bergman's rule or Allen's rule, although it's important to point out that when those people are writing in ecology, they're thinking very much in terms of just simple metabolic effects, not thinking about an agricultural nutritional channel that's temperature sensitive, right? As bad as that agricultural temperature channel is, apparently these sanitation effects can be quite substantial, right? We basically see this linear loss of child weight with higher temperatures, right? And together these things sort of tell us that from an ex-ante theory point of view, the child health costs of future climate change might be very, very high, especially when we factor in things like further urbanization, additional risks with food security, and similar. From a policy point of view, this tells us there's very high returns to targeted nutrition after things like heat waves, whether it's El Nino linked or otherwise. Right. And then along these lines, when we think about developing urban infrastructure for sanitation in tropical megacities, this is a big thing. Right. And so the fact that we end up with these very fast growing cities that then have a variety of basic sanitation problems may have these additional public health externalities that will worsen under climate change. And that's something that we think that should particularly be having some attention brought to it, because it's a somewhat underrepresented channel. And kind of echoing the work with El Nino, just child health costs should be incorporated into social cost of carbon and general climate change planning. So that's what I've got. Thank you very much for giving me the chance to present. It's great to see everyone, and I look forward to some questions.
Great. Thanks, Jesse. I'm not seeing questions on the chat or on the Q&A, so I'd ask all our attendees to please ask questions through one of those two mechanisms. What I'd suggest is maybe let's have Tama present and just have Q&A at the end to give people time to ask questions on any one of the three papers. So Tama, all yours.
Great, thanks. Let me just get my screen set up. Okay, so I think both of these prior talks just pointed us towards thinking about future climate change and the social cost of carbon. And so that's what we're going to dive into here. This is co-authored work with a bunch of my colleagues at the Climate Impact Lab, and we're going to be talking about quantifying the global scale mortality consequences of climate change. The broad motivation for this work is that the policy models that are sitting behind current climate change policy rely on really outdated information about the actual damages from climate change. You're seeing three damage functions here from integrated assessment models that sit behind the US social cost of carbon. These have been incredibly influential models, but it's increasingly clear that their empirical foundations are weak. So to make this a little bit more clear, here you're seeing a distribution of the empirical studies that sit behind those damage functions in these three models plotted against the date of publication. And these are relatively few studies, and they're relatively outdated when compared to a very large explosion of literature in the climate impact space. Two papers that you just saw fit right into that sort of trajectory of research in this area. And so we want to bring these tools and this data and this increasing evidence into policy models of climate change, in particular updates of the social cost of carbon. So we want to be guided by 3 principles when we're doing this. First, we want to be using best available empirical methods. Second, we want to reflect damage from all populations around the globe, in particular, not just the places where it's easy to collect data. And finally, we want to make projections that account for the fact that places look really different in their adaptive capacity, both across space and across time, and that investments in adaptation are costly and don't come for free. So today we're going to be focusing on following these 3 sort of guiding principles in a social cost of carbon update, but in the context of mortality consequences from climate change. The first step in this process is to gather mortality data from as many countries around the world as we can. As you will notice, that Africa is missing. And so I think there's really interesting future work to be done on combining some of the methods and the data from the papers that you just saw with the methods that we're doing here. But these are the data that we have that are comprehensive across all age groups, publicly available mortality data in the historical record. We pair those with historical observations of temperature and precipitation to estimate a very standard climate impacts regression, where we're using a suite of non-parametric controls to isolate plausibly random variation in temperature and precipitation. And what you're seeing on the bottom are average treatment effects across our sample for different age groups, where in general, we're seeing on average, this older age group above 65 shows a commonly recovered U-shaped relationship in which cold and heat both increase mortality rates. And this average effect, it gives sort of a good starting point, but what we're interested in is differential effects both across space and across time. So how do we think about that in the context of mortality? Well, imagine going to the coldest regions of the world where hot days are experienced very infrequently. What you see on the right is that we estimate a really strong response to an additional hot day in places that don't experience this heat very often. In contrast, as we move to warmer and warmer portions of the global distribution, of average climate, we see a much more muted response to one additional hot day. The hottest regions of the world are much better prepared for these hot days and exhibit a lower sensitivity of their mortality rate to an additional hot day. So thinking about this type of adaptation, we want to capture this type of heterogeneity in the historical sample to learn about what adaptation may look like in the future. And what we do is we estimate a very similar model to what you just saw, but where we allow the shape of that function to be determined by location-specific conditions. And in particular, we're going to be using long-run average climate and average GDP to determine the sensitivity of any given location. What this allows us to do is predict response functions along 2 different dimensions. So once we know a location's income and average climate, we can estimate a predicted response curve given what we see in the historical sample about differential sensitivity across space. So if we go to the coldest and poorest portions of our sample, we see a really strong sensitivity to a hot day. At increasing income levels, though, this curve declines, reflecting the fact that income enables adaptation, particularly to heat. Similarly, as we move to the right into hotter and hotter locations, we again see this curve being pulled down as hotter populations are better prepared for these hot days. This is important when thinking about spatial distribution of sensitivity today, but also when we think about projecting under climate change, as you want to envision populations moving to the right and up in this graph as economic growth takes place over the coming decades and as the population experiences warmer and warmer temperatures. So that's sort of what that behavior is what we recover in our historical sample. But then what we can do is predict across the globe what sensitivity to any given temperature may look like based on a location-specific characteristics of income and average climate. So here you're seeing those predictions for a hot day, 35C, for this more vulnerable older population across the locations where we have observed mortality records. In general, this darker red color is indicating that places that are colder and or poorer are experiencing higher sensitivity to that hot day. But the power of this model, and which is really important when thinking about the social cost of carbon and capturing the global consequences of carbon emissions, is that we can fill in the rest of the locations where we didn't have observational data to estimate sensitivity for every population around the world. Here you're seeing this done for 25,000 different regions across the globe based on their income and their average climate. Of course, in the paper, we spend a lot of effort trying to convince you that this type of extrapolation is valid, and I point people to the paper and I'm happy to answer questions about that. And so again, the pattern that we're seeing here is that poor places are seeing much higher sensitivity to heat as are colder regions of the world that don't experience these heat days very often. So this reflects the spatial heterogeneity and sensitivity, but of course we're thinking about at least 100 years into the future when we're generating projections of climate change. And so what we show is that when we carry these evolving incomes and gradually warming climates forward, we're going to experience more and more adaptation to an additional hot day, such that by the time we get to the end of century, we see a much more muted global picture in which many more places around the world are experiencing very low sensitivity, are very well adapted to these hot days. So this picture and this gradual muting of this graph reflects the benefits of adaptation that we project to take place over the coming century. But of course, this adaptation doesn't come for free. And when we're thinking about what populations have to do to invest and to achieve those adaptation benefits, we want to be able to account for the many costs that they require in order to lower their mortality sensitivity. So we're going to calculate what we want to call the full mortality cost of climate change that account for the fact that these investments are expensive. In general, the approach that we go through and then point readers to the paper, if you're interested, draws on previous work, but presents a new method that allows us to back out estimates of these costs using observed data that I just showed you. And the basic intuition for how we do this is that we make the assumption that people will invest in adaptive behaviors and technologies just up until the point where the marginal cost of doing that, of making that investment, equal the marginal protective benefits. Because I just showed you, we can observe the protective benefits in the historical data. We're going to use that observation to back out estimates of costs, even though those adaptation costs are not directly observed. So we're going to combine these pieces together, the adaptation benefits and adaptation costs, to generate projections of mortality rates under climate change in the future. And the first model I want to show you is a benchmark model in which we assume no adaptation takes place. This has largely been assumed in prior literature, and we see really large effects on the mortality rate under a high emission scenario by end of century, over 200 deaths per 100,000. This is strongly mitigated by accounting for the benefits of income growth, which lower sensitivity to those hot days. This is further lowered when we account for the fact that populations will adapt to their gradually warming climate. If we add back in our estimates of adaptation costs, we get to an estimate of about 85 deaths per 100,000 at end of century. If you want to benchmark this, you can think about the auto fatality rate in the US as about 11 to 12 deaths per 100,000. Now, of course, this is an average both across the globe and an average over a whole lot of uncertainty. And so what these represent are averages across both these 25,000 regions that we are encompassing, but also a set of Monte Carlo simulations where we capture both statistical uncertainty in those estimated dose response functions, as well as uncertainty from a suite of climate models. So each one of these regions here, you're seeing a mean effect across this, this distribution. And as you might expect, the places that are seeing really large increases in their mortality rate are the poorer places today and places that are currently quite hot. In contrast, many northern regions see declines in their mortality rate due to avoided cold day deaths. These little distributions for a given set of places show you that in some places, this distribution is really on one side or the other of zero, and we feel pretty certain about which direction this is going to go, but there's also quite a lot of uncertainty, particularly in places that are sort of in the middle of the temperature distribution. In terms of thinking about these magnitudes, on average, these effects on the mortality rate are very large when compared to current burdens of disease. So the global average effect is relatively similar to today's current burden from infectious disease. But again, this is really disproportionately borne by today's poor. So these estimates so far give us a picture of what mortality rates look like at high resolution across the globe. But ultimately, we want to be able to inform climate policy, particularly climate policy in the US, which is driven by estimates of the social cost of carbon. So we want to take these estimates and convert them into a social cost of carbon. And we do that via an empirically derived damage function. So just like those damage functions at the start of the talk, we want to build an empirically derived version of that for the case of mortality to ultimately compute a social cost of carbon. So we take those Monte Carlo simulations I just described, and we index each of them against the amount of warming from the climate model run in that simulation. Here you're seeing a high mitigation scenario, so RCP 4.5, and in a high emission scenario with a substantial amount of warming in red. And using these simulations, we can then trace out an empirically estimated damage function, which will ultimately allow us to compute a social cost of carbon. So this damage function, we use a climate model called FAIR that allows us to pulse the global climate with 1 additional ton of CO2, given that the social cost of carbon is defined as the total damages from a single ton of CO2. So when we pulse the atmosphere with a ton of CO2, this traces out into a change in atmospheric CO2 concentrations, a dynamic effect on temperature change, which then, when combined with that damage function, gives us a stream of future damages due to the mortality effects of this warming. When we take the net present value of this stream, we end up with a final number at the end of the day that is the total social cost for mortality of that 1 ton of CO2. Obviously, these final numbers are going to depend very heavily on the valuation assumptions that you make. For a variety of reasons, our preferred estimates are here in panel A in the first column, ranging from about $17 to $37. This is really important when we think about the overall magnitude of the SCC. Currently, the Biden administration is using an interim value of $52, which is supposed to encompass all damages of climate change. We're getting quite a large share of that number just via the channel on mortality. And that $52 number relies on an estimate for mortality of just $1 to $2. So all of this effort and work in trying to bring empirics to bear on this question, we are hoping can inform updates to that number, given that we're seeing really different results from what currently sits behind policy estimates. So I think I'm probably out of time, so I'll just leave my summary slides up here, and I look forward to having a conversation about this paper and also about the other two and how they relate.
Great. Thank you, Tama. Thank you, Jesse. Two great presentations. I'm not seeing questions on the Q&A, so maybe I'll ask the first question and give people time to type them into the Q&A. I encourage you to do that. Maybe I'll ask each of you a question. First, for Tama, if I remember the map of the countries where you have data from, you don't have too many countries where infectious disease is an important, particularly vector-borne disease, is an important part of the temperature and precipitation relationship to mortality. So how may that matter? And then for Jesse, I just wanted your opinion. Here we have 3 papers that are using large data sets, either from survey or administrative data, and none of us used machine learning techniques. We used parametric and non-parametric econometric estimation. And so I wonder, what's the scope as these data sets grow? What do you think about, especially for this audience, what role the machine learning techniques can play in helping us unpack some of these relationships? Tama, or go ahead.
Great questions. I also have one for you guys if you have time. So I think the short answer is you should largely think about our effects as ignoring most vector-borne disease. So we want to think about the reduced form effect in the relatively short run. So within the year of an effect of temperature and precipitation on an all-cause mortality rate. I think most of the channels, and you would know this better than me in terms of thinking really hard about how we would model the relationship between temperature and precipitation and something like malaria, are probably not coming through in that reduced form effect. And so I think largely we think of these as heat and cold induced mortality. And when we're thinking about the full social cost, we would obviously want to add to this and incorporate vector-borne disease as well.
So how would I think about machine learning showing up in this literature? I think so, Gordon, you and I and a couple of other co-authors have an evolving research agenda that's partly built on trying to apply some of this. And what I would say to anyone in the audience who's thinking about applying it is, there's the obvious analytical type approach where machine learning has a lot of potential here, in the sense that we're partly looking at the science literature to get, basically first order possible channels, and then trying to do some degree of decomposition. But all in, there's over 7 million kids worth of data in the DHS, last I counted. And if you expand the anthropometrics, it's something close to 2 million. You've got very, very large data sets here. And so I think the potential for exploratory data analysis and sort of like doing a cross check of what are these possible mechanisms, where might we expect them, let's kind of do some degree of just letting the data speak on its own and tell us what it seems to find as a general non-parametric set of relationships for temperature per se, but also specifically, I think, elucidating mechanisms. There's a lot that can be done here. But even more than just the sort of obvious, like we can use machine learning to get better predictions and think about it type of analytical approaches, I think there's a lot of potential for data generation using the machine learning techniques. And I'd say in particular when we think about things like remote sensing. And so, with stuff like the DHS, a major question that we have is, we have these amazing geospatially located child health outcomes. And then, I'll present a paper on agricultural stuff, and there we have these obvious first order questions related to something like trade. Right. And with, we have data products that already do this for us, but we now have really, really nice fine grained local spatial data with things like, road networks and, estimates of traffic and travel time and similar. And so, there's basically, I have a long list of possible working papers that are in this domain. And I think there's just endless amounts of work to be done. And so I think basically taking the remote sensing data to really help us try and understand like what exactly is going on with these environmental stressors, both in terms of what the local experience of something looks like from space, as well as tying that into other sorts of like what the adaptation looks like, what's going on with the actual like, remote sensed ag estimates and similar.
Thanks, Jesse. I think we have maybe 2 or 3 more minutes. So Tama, do you want to ask your question?
Yeah, I think both of you sort of touched on the agricultural channel, and I'm just wondering, I know Jesse, you did a bit on seasonality, but it seems like we could do more leveraging actually some of the remotely sensed products available on cropping intensity, types of crops. We know different crops respond differently to these temperature and precipitation shocks. I'm just wondering if you guys have already headed down that road, if there's a reason we can try to get one layer deeper using some of those products on the agricultural channel itself.
Absolutely. So current work with Jesse and Amir, we're bringing in the crop calendars and the dominant crops and trying to unpack this as best we can. I think understanding the different channels and eventually which policy instruments can diffuse these different channels is what the future of this literature would excite me the most. Jesse, last word?
Yeah, I mean, the one thing I'd say is we thought the El Nino paper would be a simple like, oh yeah, let's just check the short-term effect. And that was 4 years ago. So we're like, oh yes, we should have the crop calendars in.
Well, thank you very much to you both, Tama and Jesse, for some great presentations and a great discussion. Tama, there's one question for you in the Q&A. Maybe you can take that. But since we're out of time, I'll give the microphone back to Sam so that he can introduce our video speaker. Thank you all.
Thank you so much, Gordon. Really fantastic research you're all doing and a really interesting panel. I'll be streaming a video from our speaker, our World Bank speaker, Hai An Deng. He prepared this video on their research on the beneficial impacts of COVID-19 lockdowns on air pollution. So give me just a moment to share the video and we'll get started.
And we are interested in air pollution because it poses a major challenge to human health. And
Sam, we can see the slides now, so if you hit play, it should work.
It is estimated to cause more than 4.6 million annual deaths in the whole world. And most of the air pollution connected deaths occur in developing countries. So with our study, we aim to quantify the impacts of the COVID-19 lockdowns on the air quality in the context of Vietnam, lower middle-income countries. And specifically, we ask the questions if the COVID-19 lockdown could have a positive impact on the air quality in Vietnam. And if it does, how long do the impacts last after the lockdown? Put this differently, what is the duration of the impacts? And what areas with more industrial activities have more reduced air pollution? And what are the major channels of air pollution reductions? And in terms of costs and benefits, could we compare the costs induced by the COVID-19 lockdown and its benefits, monetary benefits on the economy? So Vietnam offers an interesting case study because if you look at this graph, then you can see that Vietnam air quality in Vietnam has been worsening, considerably in the past decades. So now the quality of air in Vietnam is similar, to the quality, the air quality in China, a country well known for its major air pollution problems. And so in this chart, you know, the line with the circles for Vietnam is very similar to the line with the diamonds for China. So it looks like if this trend continue, then air pollution in Vietnam, you know, can catch up with the level of air pollution in Bangladesh and India, the two countries with heaviest air pollution in the world right now. So just a quick review of our main findings. We find that the COVID-19 lockdown improves the air quality in Vietnam, and the average concentration of NO2, our main air quality indicator, decreased by 24 to 30%, 32%, roughly 2 weeks after the lockdown. However, the effects are short-term, and they tend to fade away about 10 weeks after the lockdown. And we find the impacts to be more pronounced in areas that don't have a coal-fired station or cement plants. And we also estimate some quick calculation suggest that the economic gains from improved air quality in Vietnam are roughly $0.6 billion US. So we rely on an empirical framework that uses the SAP regression discontinuity designs. So maybe I will skip over this because it is a standard econometric model now, and the intuition is that that before the lockdown, we can compare the air pollution level just before the lockdown and just right after the lockdown, because you know the lockdown is an unexpected you know, like shock happening to the economy. So by comparing the air quality level in a small neighborhood around the lockdown date, we can examine the impacts of the lockdown on air quality in Vietnam. So in fact, strictly speaking, it is a regression discontinuity design in time model. Yes. So this graph can show you that you know the lockdown date is for roughly about 2 weeks in early April 2020 in Vietnam, and the dot as the average air pollution level at the district level in the country. And as you can see, you know, if we look at you know, roughly about 2 weeks before the lockdown and 2 weeks during and after the lockdown, then the level of air quality, you know, like the level of air pollution, you know, like decreases after the lockdown. So for the data, we use district level air pollution measurements between January 1st and July 1st, 2020, provided by the European Union Copernicus program. And but right now we are updating the data to January 2021. Yes, and we also add to this air pollution database with various other you know, like data sources that we collect, for example, from the General Statistical Office in Vietnam, from the, you know, Center for Community Support Development Study, and from the UNDP and the Google COVID-19 Community Mobility Reports, and particularly we use the Office COVID-19 Government Response Checker database. We describe on the different data sets in more detail in the working papers. Yes. So for the main reasons, as you can see, table 1 shows that you know, like the air pollution, you know, like decreases significantly after the lockdown. 2 weeks after the lockdown, 4 weeks after the lockdown, or 8 weeks after the lockdown. Even though the impacts tend to decrease the further we are from the lockdown date. So for column 1 and 2, for 2 weeks, we can see that the impact is about -6. But then, you know, like when we come to 4 weeks after the lockdown, then the impacts decrease to -4. And 8 weeks after the lockdown, it decreases to -4. Yes. So in terms of We also try other model specification. For example, we look at the some linear interaction model, some quadratic model, and the results are very similar qualitatively. Yes. So not only NO2, but if we look at other air pollution measure, for example, like a CO or SO2 or O3, we also found that, like the lockdown have a negative impacts on air pollutions. But for O3, the impacts are more noticeable after 8 weeks. And when we look at some heterogeneity analysis, for example, when we look at locations without power station or cement plants, we see that the lockdown have a stronger impact on air pollution. And one possible reason is that during the lockdown, the power station and cement plants were allowed to be, in normal operations. Yes. So basically, it means that they keep, they keep working on the power plants and cement plants. They keep, they kept, like a functioning during the lockdown. So that's why we don't see any negative impact on the air pollution in the area with the plants. And if we look at some other industrial indicators, then we do see that for example, if we look at light data, right, then we do see that in areas with more industrial activity, then we do some decrease. We see more decrease on air pollution. Yes. And as an extension, or as some kind, actually, is some external validity of our RDD framework. We collect data, on the official lockdown date from more than 70 countries around the world. And we also look at a similar period. We use the same RDD method to look at the impacts of the COVID-19 lockdowns on the 74 countries around the world. And we do see that the lockdowns have negative impacts on air pollution in all the 74 countries around the world. Even though the impacts for the countries are stronger, like 8 weeks after the lockdown rather than 2 weeks after the lockdown. So this support the external validity of our model. And as some potential channel of the impacts, then we look at the Google mobility data, and we see that the lockdown decreases, like a lot of retail and recreation activity, grocery and pharmacy activities, transit activity, or activity related to the workplace. But at the same time, the lockdown is positively correlated with residential activities. So basically, it shows that, like on the channels, right? Retail and recreation, going to the grocery or the pharmacy or going to the workplace because of reduction with the activities. Then we see, the negative, correlation, the negative impact with air pollution. So this suggests that, like cutting down on the activities can help reduce the level of air pollution. So I would like to come to the conclusion, and as a main finding that I reviewed earlier. Then for Vietnam, we found that the COVID-19 lockdown significantly reduced the air pollution in Vietnam. However, the impacts are short term and disappear, roughly about 10 weeks after the lockdown. And we also found that the lockdown effects are greater in the district, without the coal power station or cement plants. And we didn't show the calculation here, but back of the envelope calculation suggests that the economic gains from improved air quality, is roughly $0.6 billion US. But this is a very conservative estimate. Yes. Thank you very much. Yes, and more details can be found in the working paper version, which is available as an IGA working paper. Yes, thank you.